Well, moles is going to be there. That's right. That's our counting device. And moles just represents a very large number of things, right? Because atoms are very small, so generally we're dealing with very large numbers of them, right? And we have things that convert to moles, from moles, and between moles, right? So what was one of those conversion things? Or conversion? Molar mass is one, right? Molar mass. And we can have that for both elements and molecules, right? Because a molecule is just the sum of all the molar masses of all of its elements. And that allows us to convert between what two physical quantities, or what two quantities? Moles and mass, right? So it's, yeah, usually it's from grams to moles, right? Those are what the molar mass converts between. And again, when we're dealing with these types of conversion problems, usually we're going to have to go into moles because moles gives us number ratios of things. So converting it to moles allows us to go between, quantities of one element or compound and another element or compound, right? So that goes between grams and moles. What was another one that we had? We had Avogadro's number, right? It was the molar mass. And Avogadro's number was equal to what? 6.022. Yeah, 10 to the 23. And what were the units for Avogadro's number? It was this, Avogadro's number represents the number of things in a mole, right? And we can remember that because it's a very, very large number, right? So it's a lot of molecules per one mole of thing. So it's usually a number of things where things can be molecules, atoms, ions, stars, galaxies. It can be whatever you want, right? Per one mole of that thing, right? And this allows us to convert between the number of things and moles, right? So you use this, for example, if you're given a number of molecules and you want to find the number of moles from that number of molecules. Or you have moles and you want to find the number of molecules from the number of moles that you have, right? And again, this is just like a counting device, just like a dozen, except a dozen would be 12 things per dozen, right? That's how we'd use dozen as a conversion factor the same way. And what was the one we started talking about more last time? The molar ratio, right? The molar ratio. And this allows us to convert between what? Moles of one substance or compound to moles of another substance, element, or compound, right? This goes between moles of A, or that can be either an element or atom, or a compound to moles of B, which could also be another element, atom, or compound, right? And the molar ratio there's two different scenarios where we get a molar ratio from, right? What are the two things that we could get molar ratios from? Say it again. Coefficients in a balanced chemical equation, right? Coefficients in a balanced chemical equation. And what was the other way we could get a molar ratio? Subscripts in a chemical formula, right? Or subscripts in a chemical formula, right? The subscripts gives us a multiple ratio of the elements within a molecule, and the coefficients in a balanced chemical equation give us the multiple ratio of two different compounds within a chemical reaction, right? And that can be from reactant to reactant, reactant to product, or product to product, right? It's anything within that chemical reaction and that chemical equation. All right, so everyone remember these? How do we feel about these quantities right now? Thumbs up, thumbs to the side, thumbs down. All right, so these are our conversion factors that we're basically doing all these just chemistry conversion, I can't remember, unit conversion problems, right? And so then we had our two different tables. This was for looking at compounds in atoms within a molecule, right? Where if you can identify what two things you're going between, you can then use our chart like this to then determine what conversions you need to do. For example, if you started with grams of an element and you wanted to find the number of molecules that you have based off that number of grams, you could then go to the moles, of the element, moles of the compound, and that gives you then Avogadro's number to get to the number of molecules of that. Or you could go from moles, go to moles of an element, then you can use that to get the number of atoms or ions, and then you can use the molar ratio to get to the number of molecules. All right, so that was one flowchart we had. This was for dealing with chemical formulas and their subscripts. And then we had the other one we were working on last time, which is where we're going to start off today, where we use the coefficients to then go usually the most steps that we can do at this point is mass of one compound to mass of another compound, right? And the steps that are involved in that is using the molar mass to go from the mass of one compound into its moles. You have to go into the universe of the moles to then be able to convert it to moles of another compound. And then you can use that to then convert it to mass of that compound using the molar mass. And the difference between both of these molar masses here is on the left-hand side here, which molar mass are we using for this conversion? For our arbitrary compounds A and B here. We're using the molar mass of A in this case, right? We're using the molar mass, I'm going to use a different color. This is the molar mass of A, because we need the molar mass of A to go from mass of that compound to moles of that compound. Where on the other side, we're using the molar mass of whatever compound B is. Right, and that's because there's not a one-to-one mass to mass relationship because elements weigh differently than other elements. Okay, so those were our charts. So let's start off with you guys then saying how many moles of ammonia can be made if you start a reaction with 125 grams of nitrogen. And here, you're going to assume excess hydrogen, right? And all that means whenever you see that is that there's enough hydrogen to react all of the nitrogen. And what we're going to learn today is that that's related to what we call the limiting reactant. We're saying nitrogen here is the limiting reactant. What's the flow chart or the conversion path you're going to follow to get here, right? What two things are you going between? Yeah, we're going to go from moles of N2 to grams of ammonia, right? And so how are we going to use our flow chart to then determine a path to convert between these things? So we're starting from moles of N2, and then what do we need to convert to? Aiden?
Starting from 125 grams of nitrogen.
Oh yeah, sorry, we're starting from grams, my bad. We're going to moles, we're starting from grams of N2. So we're starting from grams, and we go to moles of ammonia. So what's the first thing we need to convert to? We need to go to moles of N2, and then from moles of N2, we can then convert that directly to what? Yep, moles of ammonia, right? Moles NH3. And then how do we get from grams of N2 to moles of N2? What do we use? The molar mass of what? Nitrogen gas, right? And then how do we get from moles of nitrogen gas to moles of ammonia? What do we use? Molar ratio, right? Molar ratio. Which we get from the subscripts of our, the coefficients of our balanced chemical equation. Right, so now that we have the flow chart, if you hadn't done this yet, see if you can now figure out how you're going to use those conversion qualities to get the units to work out so you end up with moles of ammonia. Right, you need to make sure units are canceling along the way. All right, so we start with 125 grams of nitrogen gas, right? Then we use the molar mass. So what's the molar mass of N2? Molar mass of N2 is 28 point what? 0.02 grams N2 per 1 mole of N2. Right, so how are we going to use this to get to moles of N2? What are we going to do with this? Yep, you're going to use the inverse, right? So you're going to be dividing by that number. How do you know? Well, because we need units of grams to cancel out. 0.2 grams of N2 per 1 mole of N2. Usually, whatever we're trying to go to first, we want this to be in the numerator, right? Because that's what tells us that we're going to be left with those units there. Which means that grams of N2 cancels out. We're now in moles of N2, which is where we want after our first unit conversion step. Then we need to go to moles of ammonia. And so what's the molar ratio here? Yeah, we have 2 moles of ammonia because we get that from the balanced chemical equation. 2 moles of ammonia for every 1 mole of nitrogen gas. Right, what that's saying is for this reaction to happen 1 mole times, we need 1 mole of nitrogen gas, and that produces 2 moles of ammonia. So that's our molar ratio. We have 1 mole N2 for every 2 moles NH3. Now the units of moles of N2 cancel out, and we're left with what we want to solve for at the end. All right, when you plug that all in, what do you get for your answer? 8.92, that sounds about right. 8.92 moles of NH3. All right, so this is where we kind of ended off last time, doing mass to mole calculations or moles to mass calculations using a chemical equation, right? It's 2 steps within that 3-step flow chart that we looked at. All right, so for the quiz today, this is about the extent for what you can expect for a unit conversion problem dealing with stoichiometric coefficients. All right, we're not going to go full mass to mass calculations just yet, but you can go from moles to mass or mass to moles. All right, how do we feel about that? Thumbs up, thumbs to the side, thumbs down. Okay, so if we have at least somewhat of a grasp of what's going on here with the chemical equations, the next calculations we're going to be looking at just add another step to this. All we're doing is instead of ending in moles or starting from moles, you're going to start with mass and end with mass every single time. Right? So these are mass to mass calculations using the coefficients, right? Coefficients in the balanced chemical equation. And again, this is that flow chart that we talked about before. This is using all 3 steps. So this is equivalent to starting from grams of an element within a molecule to then finding how many grams of molecules you have from that. Or if you have a certain number of grams of a molecule, you can find out, okay, what percentage of that molecule is a specific element by mass, right? That's what you did for your magnesium oxide calculations in the lab when we used the crucible. So generally, you're going to use the molar mass to convert something into moles. Why? Because we always need to convert things into moles to go from one compound to another or one element to a compound. Then you have a mole to mole ratio, right? So this is the molar mass that we use to convert a compound A. The molar ratio is in the second step. And then once you have the molar ratio, you're going to convert that new amount of moles at your new compound into grams using the molar mass of your new compound, the molar mass of compound B. All right, so it's exact same steps we've done before. We're just adding another step to the process. So we either do one extra in the beginning or we do one extra step at the end of this calculation. But in general, it's the same idea. You can still use that same flow chart just to identify what you're going between. Okay. All right, so let's look at this combustion reaction, right? So combustion reactions, we're always gonna have oxygen, some sort of organic molecule, like in this case it's butane, and then we get CO2 and water as byproducts. So what mass of oxygen, right? So that our final answer should be the mass of oxygen, which again, when we're talking about chemical reactions, oxygen is found in diatomic form. So O2 is what they're referring to when they say oxygen. Will be required to react completely, right? That means that it uses up all of the oxygen with 96.1 grams of propane, right? So propane is our organic molecule here, according to the reaction below. So we have a balanced chemical equation. We could double check to make sure, but it's balanced if you were to count all the different atoms on either side of this reaction. And here we're not going between a reactant and a product, right? We're saying how much of the other reactant do we need to ensure that all of one reactant reacts. So that's why the molar ratios allow us not to go just between reactants and products, but also between reactants and reactants, other reactants, and products and other products as well. For example, if it was another product, you could ask, okay, if I made this much CO2, how much water did I also make? And that's another way of asking these questions. And so if we were to look at our flow chart, we would come up with something like this, where we start with the mass of propane, because that's what's given to us. So this is 96.1. You go to moles of propane, and how do you go from the mass of propane to the moles of propane? Molar mass, right? We have the molar mass, and that's the molar mass of what? Propane. It sounds like there's a baby outside. And then to go from moles of propane to moles of oxygen, right? How do we go from moles to moles? Molar ratio. And where do we get the molar ratio from? The coefficients of our balanced chemical equation, right? That gives us moles of oxygen. And then once we have our moles of oxygen, now we're adding one last step, right? The step that we didn't do before. Instead of just ending with moles of oxygen, we want to know how much is that in mass. So how do we go from moles of oxygen to mass? The molar mass of what? Oxygen, right? So if you can at least write this down for unit conversion problems, that's 80% of the way there, right? Everything else is just making sure the units are working out and just plugging in numbers into your calculator. This is the idea. This is actually the chemistry of what you're looking at. All right, any questions on making this flow chart? I'm gonna rewrite this flow chart on the next page, so it's right here, right? So we have grams C3H8. We use the molar mass, propane, to go to moles, C3H8. Then we use the molar ratio to get to moles of O2. Then we use the molar mass of O2 to get to grams of O2. All right, so we start with, what was it, 96.1 grams of C3H8. And we're going to use the molar mass of propane. So what's the molar mass of propane? How would we calculate the molar mass of C3H8? Before we, the periodic table, right? So we have 3 times the molar mass of carbon plus 8 times the molar mass of hydrogen, right? All we did is we just multiplied the molar masses that we get on the periodic table by their subscript within that formula. And so when you guys did that, what did you guys get? When you guys do that? What was it? 44.09. I'll leave it at grams C3H8. And what's the unit in the denominator? We have grams per mole, per 1 mole C3H8. And so how are we going to use this number when we're going from grams to moles? Yep, we're going to divide by this number, because if we put 44.09 grams C3H8 in the denominator, then we're left with moles in the numerator. And our units of grams cancel out, which is what we want after the first step, because we want to end with units of moles. Then we use the molar ratio. What's the molar ratio between these? Propane and oxygen. For every 1 mole of this reaction happening, how many moles of propane do we use and how many moles of oxygen do we use? Okay. Yeah, 1 in 5, right? We're saying that for every 1 mole of propane we use, we also need to use 5 moles of oxygen for the reaction to happen. If we have less, then the reaction isn't going to happen 1 mole times. It's going to happen less than that, right? And so in the denominator, we should have units of what? Yep, our propane in the denominator, 1 mole propane, because that's what we want to cancel out, per 5 moles O2. Units of moles of propane cancel out, and we're left with units of moles of O2, which is where we want for our next conversion step. And then the last step, we're doing what? We're converting moles of O2 into what? Grams. And what do we use for that? The molar mass of what? Molar mass of O2. And how do you calculate the molar mass of O2? 2 times the molar mass of oxygen from the periodic table, which is 2 times 16.00, or something close to that, grams of O2 per 1 mole of O2. And so how do we use this number then to get grams? What goes in the numerator, what goes in the denominator? We need grams in the numerator, right, which is the molar mass value, 16.00 grams of O2 per 1 mole of O2. The units of moles of O2 cancel out, and we're left with grams. So this will give us our final answer. Oops, should be 32. .00 grams oxygen. And so each of these arrows here, again, because we've said this before, each of these arrows represents one of these unit conversion steps, right? Each arrow represents one step in our pathway. You wouldn't have to go through and do an entire calculation like this. If you wanted to, you could calculate it at each step. That'll take a lot longer. But you could first convert it to moles of propane if you wanted to, then use that value to convert it to moles of O2, and then use that value of moles of O2 to convert it to moles or grams of O2. You would get the same answer. You would just have to do 3 different steps in your calculator rather than putting it all in at once. And so what do you guys get for your answer when you plug this all in? .348 point what? 49 grams of O2. And if we were to simplify that, it would just be 348 grams, oops, or 348.5. No, 348 grams of O2 if we were to use sig figs. And this makes somewhat sense, right? Because O2 and propane have relatively the same molar mass value, right? One's 32, the other one's 44. They're not that far off, but we need 5 times as much to make this reaction happen 1 mole times, right? So if we start with 96 grams of propane, we're probably going to need a good amount more of oxygen for this reaction to happen. All right, so what I'm doing is I'm just looking at the physical values. Mass-wise, those 2 molecules aren't that far from each other. If they're far from each other, then this number would deviate a lot. But they're kind of close, so I'd expect it to be roughly about, a little less than 5 times that amount. Okay, so this Next example, are there any questions on this before I actually move on? Right, or any steps that people are like, okay, I don't really understand where you get that from? I guarantee if you have that question, someone else does too. Right, like, where did you get that value from? Where does the molar mass come from? Where does the molar ratio come from? How did I know to put it in that order? Anai?
Why does the 5 moles of O2 cancel out with the 1 mole of O2?
Because the unit itself, and so that's a really good question, the unit itself is mole of O2. The number isn't associated with the unit, right? So this is you're only canceling out the unit, the numbers themselves stay. It's the same way when we cancel out any other unit. We're canceling the units out, but the numbers still go into the calculator, right? So that's why we don't cancel out the 5 completely. It's just the units itself that are canceling out. Yeah, good question. All right, any other questions? All right, so this problem already has the flow chart, right? So the flow chart is kind of the hardest part, but it already has the flow chart there. So see if you can then use the same chemical reaction to find out how much carbon dioxide will be produced, right? So before we're looking at mass of one reactant to mass of another reactant. Here we're looking at mass of one reactant to what? Mass of a... Where's carbon dioxide in this chemical reaction? On the right side of the equation, right, which is the product side. So now we're going from, well, if we have this much propane, how much CO2 are we going to have for each reaction, or 175 grams of propane? How much CO2 are we going to produce? Okay, so we're starting again with mass of propane, which was 175 grams of C3H8. First, we convert it to grams to moles of propane. Then we go to moles of CO2, and then we go to grams of CO2, right? That's the flow chart that we had. So if we get 175 grams of propane, we first are converting that into moles using what? Molar mass, which was 44.08 grams C3H8 per 1 mole. C3H8, units of grams, cancels out. And then we use what to convert to moles of carbon dioxide? The molar ratio. And what's the molar ratio between these two? 1 to 3, right? So we have for every 1 mole C3H8, we get 3 moles of CO2 that are produced, right? We know we want moles of CO2 in the numerator, so that's where we know to put that in the numerator, because that's the units that we're going to end up with that step. Then we go from moles of CO2 to our final step, which is grams of CO2. And so what was the, how do we do that? What do we use? Molar mass of what? CO2, right? Because we're in moles of CO2, we can go to grams of CO2. And what's the molar mass of CO2? What was that? Yeah, it should be about 43.99 grams of CO2 per 1 mole. We know 1 mole of CO2. We know to put this in the numerator because we want units of grams here, right? So that's where we're not dividing by the molar mass, we're multiplying by it. Moles of CO2 cancels out, and what do you guys get for your final answer? What was that? 523, let's see, 3 moles, yeah, it should be about, that sounds about right. 523 grams of CO2. And the way that I say, well, that kind of looks like the right answer, is look, the molar mass of these two compounds, very similar to each other, almost identical. The molar ratio is 1 to 3, which means I should probably need about 3 times that mass, which is probably getting around 500 is what I would expect for 3 times so that's exactly what you do, right? They're not exactly the same mass, but they're very, very close to each other. So really, if these two are about 1, you're just multiplying that number by 3. All right. How do we feel mass-to-mass calculations? A little better? Okay, so now we're going to use the mass-to-mass calculations and then actually do a series or a set of problems where we actually determine something chemically relevant, and these are going to be called limiting reactant percent yield problems. So we're actually going to be looking at, if we have a chemical reaction, what limits how many products we can make or how many reactants we need. And then we're going to say, okay, if we do have a reaction go through, how much of our reaction did we actually recover? Okay, and so this is under the umbrella term of limiting reactant. And so when we have 2 or more reactants combined in a non-stoichiometric ratio, all that means, right, so it's just a fancy way of saying when they're not equal to the coefficients in the balanced chemical equation, right? So usually you're not measuring, okay, 1 mole of propane and then 5 moles of water, and we mix those together to get the exact amount. Usually we measure something in grams and we just mix it together. So when you're mixing things in ratios that are not exactly equal to the stoichiometric coefficients, then one of the reactants is going to limit the reaction. Right, what that means is that one of them is going to limit how much of the products you can actually make or how many times that reaction can happen. Why? Because you'll run out of one before you run out of the other when they're not in perfect stoichiometric amounts. And so when that happens, that reactant is referred to as the limiting reactant. So for these problems, you're going to be finding the limiting reactant. Now, as you can imagine, this is going to be almost identical to doing mass-to-mass calculations. It's just the problems are a little longer because you have to do it for 2 different reactants for each reaction. And so before you can determine or continue with these types of problems, usually you have to determine the limiting reactant first. And so what is the idea behind the limiting reactant? Well, you use the analogy of making ice cream sundaes. Let's say for the perfect ice cream sundae, this is like our chemical equation, right? You need 2 scoops of ice cream, 1 cherry, and 50 milliliters of syrup for every single sundae, right? You need these exact ratios to make a good sundae. Otherwise, it's not a good sundae and you don't want it. So if we buy things wholesale and bulk, right? We're not going to get exactly 2 scoops of ice cream for every 1 cherry and 50 milliliters of syrup. Usually you're going to buy like a 16-ounce thing of syrup, a can of cherries, however many cherries that is, and a tub of ice cream, right? Those are in units of scoops, cherries, and milliliters of syrup. But this is how much you're going to use for each sundae. So if you had this much available to you, right, you could then determine how many sundaes you can make, right? The same way that we're looking at chemical reactions. You can determine how many sundaes that you can make, and one of these things is going to limit how much you can actually make, right? Because one of them is going to be less than the other ones in terms of the maximum number of sundaes, right? If we have 8 scoops of ice cream here. That means theoretically, if we had everything else in excess, we could make how many sundaes? Maximum amount. You can make 4, right? You can make 4 sundaes total. We have 6 cherries total. We need 2 per sundae. So we could theoretically make how many sundaes if we had a million gallons of ice cream and 1 million liters of syrup. You can make 3 sundaes from 6 cherries. You only need 1 per sundae? Oh, yeah. So you can make 6 sundaes from that, right? So you can actually make more based out of that. Yeah, sorry, I had my perfect sundae recipe off. And then we have syrup. We have how many milliliters of syrup? 100 milliliters. So how many sundaes could we theoretically make from that? 2. We can make 2 sundaes from that, right? So based off of all the ingredients you have, what limits the amount of sundaes that you can make here? It's the syrup, right? Because this gives us theoretically 2 sundaes. This gives us 6 sundaes. And this gives us 4 sundaes. So the idea with a limiting reactant is one of the reactants in our chemical equation is ultimately going to limit how much we can actually make. We will have leftover cherries and leftover ice cream in this case. But the syrup is going to be used up all the way, right? So this means that this is going to be our limiting reactant. Because we can only make, let's see if I can draw a little. I think there should be 2 cherries per sundae, but that should be times 2. Because we can only make 2 sundaes from the available syrup that we have. And so with chemical reactions, it's the same idea, except we're going to be looking instead of the moles of products being made instead of tasty sundaes, there's probably some hazardous chemicals that we'd be looking at, or pollutants for the environment. And so the general guideline for this, right, here it's easy to look at this pictorially, like as a picture, and then determine, okay, well, that's going to limit the number of sundaes we can make. Chemical reactions, we're dealing with things that are super, super small, so they're not generally easy to see. So we're dealing with things and, things that we can't directly observe. So they're a little harder to look at. But the idea here, the general process, is we're going to assume each reactant, let's say we have 2 reactants, are limiting reactants, and we're going to calculate the theoretical amount of moles that we can make of our product. Right? So you start with reactant 1, for example. You use that to convert it to moles of reactant 1. Then you use that to convert it to moles of the product. And then you keep that value, so you store that value. Then you assume the other reactant is limiting, so convert the grams to the moles of reactant 2. And then you use that for the moles of the product. And then you compare these 2 values. Whichever one is less is what's limiting the reactant, right? Because one reactant can create more moles of product than the other one. So the one that can create less is ultimately going to determine which one you can actually make, right? And then to determine how much you actually make with that reaction, you convert the moles from the limiting reactant to the product, right? Grams of the product in that case. So this is just doing a mass-to-mass calculation. At first, you do 2 different mass-to-moles calculation to determine which one is limiting. And then you, in the final step, convert it to the mass. All right, so here, so I saw a lot of the smiles go away when we stopped talking about ice cream and got back into chemical reactions there. This is the mass to moles calculation. And you're just doing that 2 times. And then this is just converting the moles to the mass of product. But overall, you're just doing a mass-to-mass calculation like we just did. The only difference is now we're looking at both reactants in this case to then see which one is limiting the reactant. And so when we're going from grams of reactant 1 to moles of reactant 1, what do we use there? When we go from grams of reactant 1 to moles of reactant 1, we use the molar mass, right? This is the molar mass of reactant 1. Then we use the moles of reactant 1 to go to moles of product. What do we use to do that? The molar ratio. Whenever we're going between moles and moles, we use the molar ratio, right? The molar ratio. And then on the other side, it's the same thing. The molar mass of reactant 2 and the molar ratio between them. Once you determine what the limiting reactant is, then how do you go from moles of product to grams of product, sorry. Then you use the molar mass of the product itself. All right, so again, this is identical to everything we've done up to this point, just an extra step, right? It's combining 2 problems into one, basically. All right, am I good to go on? Okay. Sam?
What if your assumption for both of them is like wrong?
Well, you just assume both, and then your assumption tells you which one is correct.
Like if you had 4 and you chose like 2 and 3, but in reality.
If you had 4, then you have to do it 4 times. You don't do it 2 times.
Okay, I see.
Right? So you don't know until you test all of them.
Good question.
So this is for only two reactants. All right, so I know what the makeup quiz assignment will be. The 6 reactant reaction. You'll learn how to do mass to moles. All right, so here we have an example. How many moles of H2O, so this is way a limiting reactant problem can be phrased. How many moles of H2O water can be produced by reacting 4 moles of hydrogen and 3 moles of oxygen as shown below? Right, so we're asking, we have these two non-stoichiometric amounts. How do you know? Well, the mole amounts aren't equal to the coefficients, right? So they're not, it's a non-stoichiometric amount that's being made. This is an easier calculation because we're not going from grams, right? We're not starting from grams. We already have everything in moles. We have moles of reactants, which means for each of the reactants, we need to convert it into what? Convert moles reactant to moles of what? Product, right? Because that's how we're going to test to see what's limiting this. What limits the amount of product that we can make? All right, so let's look at hydrogen first. We have 4 moles of H2. How do we go from moles of reactant to moles of product? What do we use? Molar ratio. And what's the molar ratio here? It's 2 to 2, right? Which is like a 1-to-1 molar ratio, but we have 2 moles H2 per 2 moles H2O. Right? We get that from our balanced chemical equation. And so this is just going to equal 4 moles of water that's going to be produced here. Right? Because 2 over 2 is just 1. We're just multiplying that number by 1, which is how I know it's going to be the same there. Then we also have to do this for oxygen to see if oxygen then limits the reactant. So oxygen, we start off with 3 moles of oxygen. What's the molar ratio for oxygen to water here? 2 over 1, 2 moles H2O per 1 mole O2. And so now we're going to make 6 moles of H2O. All right, so which reactant here limited the number of sundaes we could make? Hydrogen, right? Because theoretically we made less products. This is less moles than water, less moles of water from hydrogen than moles from oxygen, right? Theoretically, we have more oxygen present than needed to react 4 moles of hydrogen gas, right? So because this is smaller, that means that H2 is the limiting reactant, and only 4 moles of H2O will be produced. Right? Because we mixed basically excess oxygen with 3 moles or 4 moles of hydrogen gas, that means that hydrogen is going to determine all of the water that's produced in this reaction. All right, so in our ice cream example, this would be like the milliliters of syrup, and this would be our conversion from milliliters of syrup to number of sundaes that we can make, right? 50 milliliters per sundae. This would be like our scoops of ice cream, and this would be our 2 scoops of ice cream per sundae, right? Make 6 sundaes here, 4 sundaes there, right? This limits the number of sundaes that we can make. So hydrogen is our limiting reactant here. Okay, any questions on this? Right, so this is a simple calculation. We don't really have to plug anything to our calculator because Everything's in whole numbers here, right? And it's not going between grams of reactants here. You're already given the moles. If we start with grams of reactants, we have one extra step to convert that into moles first. All right. So here we have a more complicated example. We have a fuel mixture that's used early days of jet fuel and rocket fuel. And we want to know how many grams of nitrogen gas is produced when 100 grams of dinitrogen tetrahydride and nitrous oxide are mixed together. Right? So now we know we have non-stoichiometric amounts because everything's given in grams, right? So we know automatically that's not going to give us exactly 2 moles of this and 1 mole of that, right? So because they're given to us in grams, now we're going to have an extra step compared to the last problem, right? So the first step here is going to be what? It's still going to be the same first step. There's just going to be extra steps involved within the step. Stepception. Or what's the first thing we have to do for these problems?
Convert grams to moles.
Yeah, we're going to have to convert grams of each reactant into moles of product, right? Convert grams of each reactant to moles of nitrogen, right? Because that's what we're actually looking at here, right? How much nitrogen gas are we going to create? Right, so that means for N2H4, where we start with grams of N2H4, we convert that to moles of N2H4. We convert that then into what? All right, once we get this one, right, we're looking at this reactant, bless you. This reactant first, we're converting them to moles of N2H4 because ultimately we need to calculate the moles of what? Of nitrogen gas, right? So that means after we get this into moles of N2H4, we're going to convert that into moles of what? Moles of nitrogen gas, right? Moles N2. And to go from grams of N2H4 to moles of N2H4, what do we use? Molar mass, N2H4. And to go from moles of N2H4 to moles of nitrogen, then we use what? The molar ratio. Okay, so see, spend the next 5 minutes or so to see if you can do this for each reactant, right? It's going to be the same idea for the other reactant, just the molar mass that you're going to use and the molar ratio will be different. I'm going to see if I'll just calculate. So we have 100 gram, 4, this be 32.05 over mole and H4. Two. Then we'll do. I'll go back in a second. That was 1 mole. 04. That's 1 mole. 1 mole for 3. Okay, so for the first step, right, we calculate the theoretical amount of moles from each reactant. Here we did it for dinitrogen tetrahydride, and we used the molar mass and the molar ratio to convert to moles of N2. We see we make 4.68 moles of nitrogen gas when we do that. We do the same thing for nitrous oxide, and we see that for 200 grams, we use the molar mass of nitrous oxide to convert that to moles, and then the molar ratio to convert that to moles of nitrogen gas. We get 6.52. So which one is our limiting reactant here out of these two? The first one, right? Because it makes less moles, right? Because it makes less moles, that's our limiting reactant. That means that when we mix this mass of each reactant together, only the mass of the limiting reactant determines the products that we make. So the next step is to convert moles of the limiting reactant to mass of product. The moles of N2 from the limiting reactant, right? The moles of N2 that we made from the limiting reactant, which was 4.68, right? So we had 4.68 moles of N2. How do we use that to convert to grams? What do we use? Molar mass of what? Just N2, right? Because we're converting moles of N2 into mass of N2 because it's asking how much N2 is produced. And to determine the limiting reactant, we had to convert it to moles of N2 to see which one theoretically makes less moles. The one that makes less moles determines the amount the reaction will actually make when we mix them together. So we use the molar mass of N2. And we're going to multiply the molar mass so that the units of grams are in the numerator, right? So I believe it was 28 point, what was it? 02. What do we have over back here somewhere? Where? .02 grams of N2 per 1 mole of N2. So we do 4.68 times 28.02. And that gives us 131.1 grams of N2. That's how much nitrogen gas was produced in mass. That's the mass of nitrogen gas that's produced in this reaction. Right? So the first step is we have to determine which one is going to, which one, like our syrup, which one's going to limit the number of sundaes we make. The moles of N2, which is the product that we're looking at, is what we need to figure out is what's making less of that. We see that the first reactant is what makes less, which means that we're going to convert this amount into the mass of nitrogen, because that's the actual mass that's gonna be made in the reaction. The theoretical yield of this reaction is what it's called. Okay, so we'll stop, huh? Yeah, go back. I'll leave it right here. So we'll stop there. We'll start the quiz at 3:30 in lab today. So I'll give you guys a little bit extra break because we went a little over today.